Hi and welcome to Spectrum. Today I would like to talk about color. Color is a very simple and very complex phenomenon at the same time. Everyone can talk about color. Everyone can say it's red, it's green, except obviously blind people and some people who actually cannot see color. But for most of us, it's a rather simple process. The complexity of it comes really from physics. You have photons, and I won't go into the details, but really you have photons, and they go with different wavelengths, and they either go through objects if they are translucent, or they bounce on objects, and ultimately that gets into our eyes, and it reacts with the retina. There is a chemical reaction that gives an electrical signal, and all that gets processed in our brain. I mean, this is really cool. If you think about it, it's a really cool thing. But ultimately, as humans, we wanted to do maths with that, and we needed to have numbers. So I'd like to explain you what was this experiment done in the 30s, where you had a bunch of guys that asked to look inside a tube, and at the bottom of the tube, what they had is this. It's on one side you have half of the surface that is actually a light going through a gel, and it gives a color. And on the other side you have an additive system with red, green, and blue. And the guys had knobs, potentiometers, to change the balance of the power of those different lights into the mix, and were asked to reproduce on the right side what they had on the left side. And out of this experiment, what we got is actually statistics. And this is great because technically, based on that, I could say, okay, this is, well, it's actually quite crazy because based on a physical phenomenon, you're able to describe with numbers the reaction and the sensation. And I find it to be fascinating because ultimately we managed to put our sensation, our perception of the world, of a very complex phenomenon into numbers through this experiment. And if you take those statistics and flatten them into because you had X, Y, Z, so 3-dimension, and bring it to that, you get this, what is called the CIA 31 chromaticity diagram, and that gives you this horseshoe shape where you have the visible spectrum. So because technically what you have in here is this. It's literally all the colors that are emitted and that we can see, because obviously you have the ultraviolet, but we cannot see them, and the infrared that we cannot see them either. If we can bring it back in here, in fact, if you look at the outside of this shape, you have all the wavelengths corresponding to colors. But what is even more fascinating is actually this straight line, which is the violet, because as opposed to what you have, for example, if you look at 630 nanometers, you'll have a color that would be something like between orange and red, but violets don't exist. And this is crazy because we're talking about colors, and we have a sensation of colors and everything, and really our brain and our sensation and perception of the world is designed for us to survive in this world, to be able to express and things. But it's actually extremely interesting to have these things that are not continuous, that are on a straight line, to be actually attached together to make our sensation. And really, I think this experiment is extremely important because it's a fantastic way to describe how we can get the world into codes, numbers. Across the year in color science, we've made the model of representation evolve, and we have different ones depending on the use case. So for example, if you're working with paint, or if you're working in digital picture cinema, you have different representations model. And that was really the foundation of my reflection on how we could use this as an example and actually a tool set for other things than just color. So I hope that you enjoy this presentation, and I hope that you'll be interested in the following of that reflection around how to describe the word and put it into numbers. Thank you.